We're going to be looking at section 13.4 today. That's the law of sines and also some formulas for finding the area of non-right triangles. So let's start with this triangle over here, triangle ABC. And one thing we can do with triangle ABC if we draw in this altitude, this height, is we can find it by looking at the sine of this angle. So here's my triangle right here. And it's a right triangle. So I can do the sine of angle A equals opposite, which is H, over hypotenuse, which is B. And then if we want to solve this for the height, we'd multiply both sides by B, and we'd get H equals B sine A. So now that we know the height of this triangle, we should be able to combine it with the formula for the area of a triangle, which is area equals 1/2 base times height. So area equals 1/2 the base times the height. Our base is, let's see. Our base is this guy right here, C. And then our height is this guy right here, B sine A. So what we've just come up with is a formula for finding the area of a triangle that's related to two of the sides, B and C, and then the sine of one of the angles. So we can write that as half the product of two sides times the included angle. So hopefully you remember from geometry that the included angle means it's the angle between the two sides. Okay? So it's between the two sides. So because we're not specifying which sides you have to use, there's different ways that you can write this formula. So for instance, you could put 1/2, and then if you choose sides B and C, then you would take the sine of the angle between them, which would be sine A. If you choose sides A and B, then you'd have to take the angle between them, which would be angle C. If you choose sides C and A, then you'd have to take the sine of the angle between C and A, which would be angle B. So you can see there's three different ways to write this formula, and what it does is it means that we can find the area no matter which sides or angles that we're given. So let's go down to the first problem. Okay, so problem number 4, which is actually problem number 1. Okay, so I'm going to do area equals 1/2, and then notice that they're giving me two sides, this side and this side. So this is going to be 8, and this is going to be 12. And then it tells me that the included angle, that means the angle between those two sides, is 135. So I'll multiply this by the side of that included angle, 135 degrees. Okay. So if I multiply this out, I get 48 times 1 over root 2. Remember, that's the sine of 135 degrees. So I do 48 divided by the square root of 2. And we get that the area is equal to about 33.9 meters squared. So the next thing we want to do with sines is we want to come up with a formula so that we can use sines to work with triangles that aren't right triangles. So this is something that's known as the law of sines. And basically, you can think of it as like triangulation, where you have known distances from three objects and you're trying to find out where is that distance. Okay, so we're going to use this to work with non-right triangles. In other words, oblique. Oblique triangles are non-right triangles. And there's certain kinds of information that we have to have. So one of the ways that we can solve these problems is if we have two angles and then any side. Okay, so I could have these two angles, and then I could have this side, or I could have these two angles, and I could have, let's say this time the side across from him. So any two angles and any side. Okay, or we have what's called side-side angle. Side-side angle is when you have two sides, and then you have to have one opposite angle. So an opposite angle means the angle across from the side. So if I had this angle and this side, I could have any other side. So this would work, yes. But if I had this side and I had this side and I had this angle, that is a no, because I don't have any of the angles that are across from the two sides that I have. So I couldn't use that method. So let's look at how we come up with the law of sines. The law of sines is derived by looking at the three formulas for area that we previously talked about. So those formulas were 1/2 BC sine A, 1/2 CA sine B, and 1/2 AB sine C. If you divide all of these formulas through by 1/2 ABC, let's look and see what happens. The 1/2s cancel, the B's cancel, and the C's cancel, and that leaves me with the sine of angle A divided by side A. Let's do the same thing for the middle one. The 1/2s cancel, the C's and the A's cancel. That leaves me with the sine of angle B divided by side B. Lastly, the 1/2s cancel, the A's cancel, and the B's cancel, and that leaves me with the sine of angle C divided by side C. So this right here is the law of sines. It's a really powerful formula. It works for any triangle. It doesn't have to be a right triangle. Okay? And one thing that's cool about the law of sines is you can flip it upside down. What I mean by that is you see on the bottom here we have A, B, and C. These are all the sides. We could flip it and put all the sides in the numerator and put the sines of all the angles in the denominator if we wanted to. All right, so let's use the law of sines to solve some problems. Okay, let's look at this guy right here. Problem number 1. One of the things I need when I set up the law of sines is I need angles across from sides. So here's a side and an angle that are across from each other. So I notice that I have side C and I also have angle C. So I should be able to use that guy. That's going to be 14 over the sine of 82 degrees. And then here's something that I also have and something that I want. So I want side A, and I could put it over the sine of angle A. So when you have a problem like this, all we're going to do is cross multiply to solve for A. Should get the sine of 64 times 14 divided by the sine of 82, and you get A is approximately 12.7. Since this says solve the triangle, that means we need to solve for all the sides. So I could set up another proportion with the law of sines. This time I could do 14 over the sine of 82, so in other words C over sine C, equals B over whatever angle B is. Now how am I going to find angle B? Well, angle B should be easy to find because A, B, and C add up to 180. So that means that angle B has to be 34 degrees. So now I can take this guy and I can cross multiply this proportion, and again I can solve for side B, which is going to be 7.9. Okay. Now take a look at problem number 2. In problem number 2, there's no picture drawn, so it can be really helpful to just do your own quick sketch. Make sure you label it so that you put things across from the right parts of each other. So for instance, if this is angle A and I put 50 degrees, and angle C would be 33 degrees, and then in between those would be B, which would be 76. Right now you'll notice we have 2 angles and a side, but we don't have any angles and sides that are across from each other. So we find these fairly easy. We know that angle B plus angle C plus 33 have to add up to 180. If you solve that, you'll find that angle B equals 97 degrees. So now we can set up a proportion that looks like side B over the sine of B equals side A over the sine of A. And again, I'm going to cross multiply here and solve for A. I get A equals 59.3 degrees. And I would solve in a like manner for C, side C, this little side right there. All right, so now let's go down and talk about the next portion of the lesson, which is the ambiguous law of signs. So if you're not familiar with the word ambiguous, it basically just means unknown, that you're not really sure. And the reason why we have something called the ambiguous law of signs is because sometimes when you're working with the law of signs, you're not really sure if the angle you're getting is the correct answer or if there could be another answer. Kind of like when we were working in class and we were saying the sine of an angle is a half, what's the angle? And we weren't sure if the answer was going to be in the first quadrant or in the second quadrant. So we're going to look at a couple of different problems, and I'm going to show you how when you work through these different problems, you can either get one solution, you can get 2 solutions, or you could get no solution. So as you work through these problems, the ambiguity comes in as to which one of these outcomes we're going to have. Are we going to have 1 triangle, 2 triangles, or no possible triangle? Now, if you look in your book, there's a whole section which tries to tell you how to know which of these problems you're coming upon before you even solve the problem. I think it's sometimes easier just to set the problem up and work through it algebraically, and the answer usually reveals itself pretty quickly. So let's look at the first one. Looking at the example, I'm going to start with the sine of 30 degrees over 20 equals the sine of angle B over 16. So I'm setting up the law of sines, I'm cross multiplying, and I get angle B equals 24 degrees. So why is this problem ambiguous? How do I know that the sine gives me 24 degrees and not a 24-degree reference angle, in which case angle B could be in the second quadrant and I could get 156 degrees? How do I know if B is 24 degrees or 156 degrees? Imagine if angle B was 156 degrees. What would that leave for angle C? If you take a look at angle C, you'll notice that if you add 30 and 156, you get 186 degrees. So clearly, this guy right here cannot be the answer, or there wouldn't be any angles left to come up with angle C. So the quick check here was that when we looked at our original angle, angle A, and when we looked at a possible solution for angle B, 156 degrees, we saw that they exceeded the amount of degrees that could be possible in a triangle. Therefore, the answer must be 24 degrees, and there's only one triangle possible in this example. Let's go down to example number 2. In example number 2, it's possible to get 2 different triangles when we solve this problem. Let's see how it works. I'm going to start with angle B. I'm going to get 17 over the sine of 16 degrees equals 24 over the sine of angle C. When we cross multiply and set up this problem and solve for angle C, we get that angle C equals about 23 degrees. So again, how do we know if angle C is in the first quadrant, a 23-degree angle, or if angle C is a reference angle and it's actually a 23-degree reference angle in the second quadrant, making angle C equal to 157 degrees? Well, let's check. What would happen if our original angle, angle A, which was 16 degrees, was added to 157-degree angle? Do those two things add up to 180? Actually, they don't add up to 180. They're just shy of 180, which means that it's possible to have enough degrees left over to come up with a measurement for angle C. So when I looked at these measurements, I found that there was plenty of space to still have angle C. So my two answers are, I could have one triangle where angle C equals 23 degrees, or I could have another triangle where angle C was equal to 157 degrees. Last case for the law of sines, ambiguous case. Looking at some triangles, the sides that they give you are too short. You notice that if you come up with a side in a triangle that's too short, it isn't long enough to reach the other side and make an angle. And this happens sometimes. Okay? So if I was looking at this problem over here, I would set this up by doing 15 over the sine of 80 degrees equals 25 over the sine of B. When you cross multiply here and solve, you end up with something very peculiar. You end up trying to take the inverse sine of 1.64. Remember that the maximum value of the sine is 1 because it's in a unit circle. So therefore, B cannot exist. And you'll see that you get a domain error on your calculator, and therefore these problems have no solution.